So, as I mentioned before, the quizzes that are on D2L are there to practice, so there's not a grade for those. But do go to them and practice them and make sure you're good, because I make my test literally off of those types of questions, so there's no surprises off the test. So last time, you guys realized, what is this, a third week of class, and this is only our second lecture? Like I did introduction day, then we did the ACS test, then it was NMLK, and then it was this weather thing. It's so weird. 3 weeks in, I feel like we barely started. But I know I was putting y'all to sleep last time. A lot of y'all knew this stuff from previous experience. If you're not that comfortable with this stuff and you're just afraid to speak up, definitely come see me. There's also going to the, what do you call it, the tutoring center. They can help you. But the best thing to do is just come see me. My office hours are 2 to 3:30 on Tuesdays and Thursdays. If you can't come then, just email me and we'll figure out a time that works for both of us. But what I'll do is I'll go over some of these questions that I put on D2L, and then we'll just move on. But I do want to actually do some calculations instead of just speaking about everything in theory. So I can actually see how many people can access this. I just opened the density one. I meant to have that one open. But let's just kind of... So this number, the first one, so significant figures basics. Question number 1, how many significant figures is that? 23.40. It is 4, the 0 counts. How many significant figures? 233.42, how many? There's no zeros, so it's easy, you just count all of them there. Question 3.000456. That was 3, the leading zeros don't count. 4 and 5, how many significant figures are 4? 2. Without a decimal, those zeros don't count. But question 5, how many? I wrote these questions myself, and there are mistakes. If you see something you think is wrong, I can change my answer key. Sig figs for multiplication and division. Pull out my calculator. And question 1, 23.050 times 34.2. That's what my calculator says, but what should I report as the answer? How many significant figures should it have? So you've got 1, 2, 3, 4, 5 significant figures, and then you got 3 and then 34.2. So that means we're going to keep 3, keep those 3. We look one more out to decide whether we round this digit. That's a 3, so 7, 8, 8 should be the answer. You guys comfortable with that? What's 12 divided by 3? 4. This is a simple math. You don't even have to pull out your calculator. But what should we write as our answer? You need 2 significant figures in our answer because of the 3.2. So you don't just write down 4, you write down 4.0. You sort of force it to have that second digit. You guys comfortable with that? Addition subtraction rule. All right. 45.67. Just going to go through these kind of quick. 45.67. This is question 2 of the addition subtraction rule. 45.67 minus 12.3. My calculator says. So what do I want to write down as my answer? What'd you say? 33.4, right? Is that what you're saying? The 45.67 has 2 after the decimal, the 12.3 has 1 after the decimal. So that's what we want to keep, 1 after the decimal. The 7 rounds to 3, so it's 33.4. You guys comfortable with that? Anybody feel lost? I think y'all are good. Want to move on to stuff that doesn't put you to sleep. So question 1 is a metric to English. You know how to set up? Put this up, or I'll keep this moving. And convert that to liters. So you convert, it says this, 1 gallon equals, I will always give you these conversion factors. Like I said last time, whenever you see it written like this, this is just how it's tabulated. You're going to use it either like that, or you'll use it like one of those 2 ways. It depends on what you've been asked. We're given 3.0 gallons. That means we want gallons on the bottom and liters on the top. That should say gallon. So it's this one we're going to use. That makes the gallons cancel out. This is exact, so we don't need to consider those for significant figures. From here it's multiplication. 3.00 times 3.785. My calculator says, and of course the gallons cancel, so we're in liters. But what do I want to put down for my answer here? What do you say? 7.4. 3 significant figures, 4. So I'm going to keep 3. I'm going to look at the 5. The 5 rounds that 3, so it's 11.4 liters. Answer there. So if you're having trouble with these, come get some help from me. Density, I didn't have this open before, but I meant to. Density in general is mass over volume. And we tend to use, in science, you'll either see it as milliliters, grams per milliliter, or you sometimes see it as kilograms per liter. We usually use this in a chemistry class. So the mass unit is grams, the volume unit is liters, with the appropriate prefix, but just realize so that's a mass over a volume, that's still density. See what I'm saying? So this is the general fact about density. All right. When it comes to questions about density, density is, okay. Realize you've got density, and let's just stick with grams per milliliter. That would be the units. It's going to be grams over milliliters. And let's say X grams over Y milliliters. There's 3 values here. There's the density, it'll have grams per milliliter. There's mass, It'll have grams, and there's a number for the milliliters. 3 values there. If you have 2 out of 3 values, you can always solve for the third. You see what I'm saying? So when you get questions about density, you'll either be given this and asked to calculate density, or you'll be given the grams and the density and asked to calculate the volume, or you'll be given the volume and the density and asked to calculate grams. There's only 3 ways to ask this basic question about density. See what I'm saying? You guys good? Am I still putting you to sleep? We'll move on to atoms. Question 1 in the density. Density of 0.65 grams. I think I said this last time, but if you see for your density, this just tends to be the way we write it in a sentence. Go ahead and break it out into this. The unit on the top, this value always goes with the unit on the top, and the number that goes with the unit on the bottom is always a 1, and that's always exact. That's 2 significant figures, and that's exact. So here you're given density and 80.0 milliliters, and it should say how many grams. Oh no, I have to fix these. I used, last semester, I used ChatGPT to write questions for me. And I work with it, and I say, okay, give me 10 questions on density. Give me 10 questions on density. I go through it carefully and go, yeah, you did it right. All the A, B, C, and D, that's all right. And I was like, okay, cool, give me 100 of those. And every time, when I'll get 10 correct, and I'd say, okay, now give me 50 or give me 100. The first 10 would be correct. And from there on, it would just make stupid mistakes and stupid mistakes and stupid mistakes. So I gave up on ChatGPT. I kept some of these and edited them. But apparently, so let me hide that. I'll fix it. No, I'll keep using it. So let me just do a couple of these. Okay, some of these still have mistakes. Is this the one I opened before? Where did I get those numbers from? Is there another density thing? Oh, I know what it is. It's pooling the questions, right? I do still have it linked to like 50 questions, and then randomly grabs 5 anytime you click on it. So I have to go back and fix it. But let me finish this one. If you're given this 0.65 grams per milliliter, realize you want to turn it into that, and then you're given milliliters, and now you're asked to give grams. So if I have 80.0 milliliters, and it's 0.65 grams to 1 milliliter, that's how you do it. That's exact, 2 significant figures, 3 significant figures. Multiply my calculator just says 52, so it automatically did the significant figures for me. But 3 significant figures, 2 significant figures, we need to have 2 here, so it's not 52.0, it's 52. I can make up questions. Let me fix that one on this and I'll open it again. All right, this is a case where you're given and you're asked for volume. So that's one of the ways you can get this. Sometimes you'll be given. You guys will remind me. I mean to leave that there for the people in the back so they can see, but I forget to turn it back on. Okay, what if you're given volume? just make up one. Let's say you're given that for density, grams per milliliter, and let's say you're given that in milliliters. You're still going to start with 13.64 milliliters over 1. This turned into 0.971 grams to 1 milliliter. No, that's the one that did before. Yes. So it's the same as the one before. Since I need milliliters on the bottom to make milliliters cancel, to come out to grams, so I happen to be doing this one here. This one would be, how many significant figures does my answer need to be? It's 3. 4 here, 3 here, I'm multiplying. That's what my calculator gives me. The milliliters cancel on the grams, so if we're keeping 3 significant figures, it's those 3. The 4 does not round the 2, so 13.2 grams is the answer. Now I'll do one of these. Let's say you're given for density grams per milliliter, and then well, we need to do volume, and this one. And let's say we have grams of it. You're going to start with the grams over 1. This again turned into 0.8416 grams over 1 milliliter. And in this case, we need to invert this to make the grams cancel, give us milliliters. Right, 0.8416 grams to 1 milliliter. Now we're dividing, but it's still the multiplication division rule. 3 significant figures, 4. So my answer needs to be 3. 19.4 divided by 0.8416. My calculator says 3 significant figures, 4. There's 3. We look at this next one out, it does round, so we go 23.0. Grams cancel, we're in milliliters. The answer. The third way is you're literally being asked to calculate density. You're given and you're asked. So in this case, you'll be given something like, I have a solution here, and it weighs 21.6 grams. And its volume is, try to keep these realistic, 22.61 milliliters. Then you're just going to go 21.6 grams, 22.61 milliliters. The units will just be grams per milliliter on the right, and then you just do the division. 21.6 divided by 22.61. My calculator says 0.955,329, blah, blah, blah. 3 significant figures, 4. We're going to keep 3, those 3 grams per milliliter. That's your answer. You guys okay with this? I'm still boring now, right? What else do I have in here? The quizzes. I need to go back and look at these. So I can tell not everybody's looked at these, but do look at them. Make sure you're comfortable with this stuff. Okay, next thing I want to do. You can kind of get out of this numerical stuff. Make it feel like a chemistry class. If you have taken chemistry in high school, everything's going to look so familiar for the first few weeks. But I'll still go over it. But let me again tell you, the roadmap for this class is, we always start with calculations. That's generally chapter 1 in any chemistry book, okay? And we're kind of past that. And then we talk about atoms, and now it feels like a chemistry class. Atoms, you learn about the atoms. You learn about protons, electrons, and neutrons. That I'll just do P, E, and N for. Actually, the symbols, kind of the official symbols. I like that. You learn about those in the atom. You learn about the periodic table. And a subject that lends itself very well for on atoms is ions. Ions versus neutral atoms. This all sound familiar? Ions. And then there's calculations into the atoms, and then there's this. Atoms come together and form what we call compounds. So we talk about atoms as if they're individual little things by themselves. And you only think about them like that. And then you go, okay, in the real world, most atoms don't exist this way. They exist aggregated somehow in what we call compounds. The 4 compounds in the universe, I think I said this already, but there's ionic compounds, covalent compounds, metallic, and coordinate covalent. Those are the 4 types of compounds that exist throughout the universe. We don't talk about these in here. I just like to, since there's only 4, I like to show you the whole list. This comes up a little bit, but that's still another subject for really 12-12. But metallic compounds are things you think of as metal. This is metal, I think. For some reason, there's a $0.50, either $1 or $0.50. That's metal. Anything that goes clang is metal. But we really don't talk much about it. So really, we talk about calculations. There's atoms, and then there's ionic compounds, and we talk about them in their own little places, covalent. So this is ions, formulas. I generally do ionic reactions. Solubility. So that there's a handful of things that you can discuss with ionic compounds. Covalent compounds are and a few other things. So just kind of to put a roadmap in your head. There's calculations, introduce atoms, and then we could really go here or here. Like we could go here and discuss this for a bit, and then after a couple of weeks of that, we'll go here. But it really doesn't matter which way we go. These are kind of equivalent. It's just we're talking about the main compounds that chemists deal with. But since ions is kind of a natural subject to discuss when you're learning about atoms in the periodic table, I generally go here first. Talk about ionic compounds for a little bit, and then after a week and a half or so, then I go here. So as a roadmap to this class, just to organize in your head where we are, I'm here now. I'm going to talk about atoms in the periodic table, and then we'll get to ionic compounds next. You with me? Are you awake? Okay, so atoms. has anybody not heard the word proton, electron, neutron? Those are the only particles we deal with in chemistry. Apparently, those are made up of even smaller particles, but you'd have to take a physics class for those, and I don't know much about that stuff. I'm a chemist, that's why I stopped. I don't look any deeper than that. Protons have a positive charge, electrons have a negative charge, neutrons are neutral, they're not positive or negative. The key about positive negative is positive particle and a negative particle will be attracted to each other. A negative particle and negative particle repel each other. And a positive particle and a positive particle repel each other. That's the electrostatic force. In an electron, in an atom, you have protons in the center, what we call the nucleus. And you have electrons out here in what we call orbitals. We'll talk a little bit more about orbitals later, but just have a picture in your mind. Protons are concentrated in the center, and then the electrons are floating around the outside. Here's a couple of additional facts about protons and electrons. Electrons, they do repel each other, but if they manage to get close enough to each other, they will stick. But you can only have 2 electrons together. You can't get 3 together, you can't get 4 together, you can only get 2 together. And what's going on really, an electron has what we call a magnetic pole, and that's what does it. So you've got electrostatic force, the negative electrons, but if they get close enough, the north-south poles will stick to each other, and that's how you get individual electrons to stick to each other. But you can't get 3 to stick together, you can't get 4 to stick together, it limits it to 2. Protons, if you manage to get them close enough, you can have a proton and another proton stuck together. But then you can also get another proton stuck to that, and you can also get another proton stuck to that. You can stack these, you can only get these in pairs. You can only get pairs of electrons. For protons, up to about 100 protons can aggregate together. You with me so far? Logically, so far what I've told you is the universe is made up of, there are electrons around, and then there's a proton by itself, and over here there might be 2 protons together, and over here there might be 3, and then 4, and then 5, all the way up to 100. You with me so far? You are right. Okay. If there's a proton sitting by itself, somewhere in the universe, an electron is going to get attracted. And those two, once they come together, this overall system, do picture the electron going around. But this thing is now neutral. It's got just as many positive charges as it has negative charges. So if I have this just sitting by itself, it has an attractive force to negative particles. And if I have this just sitting by itself, it has attractive force to positive particles. But once these come together and form this, now out here I can have an electron here, a proton here. This is neutral now. It doesn't attract the negative, and it doesn't attract the positive. It's just neutral. You with me? You guys good with that? But of course, based on what I just said, somewhere out in the universe, there's 2 protons stuck together. So what's that going to attract? Well, it's going to attract an electron to go around it, but it would be positively charged right now. This negative charge neutralizes one of these positive charges. So this overall thing, as I've got it drawn, still has a positive charge with it. Do you follow that? One negative charge, one positive charge neutralize each other. The other proton that's there has another positive charge. So this overall thing is still positively charged. So we have protons floating out in the universe, electrons floating out in the universe. It's going to attract one more negative charge because it's positive. But once one more electron comes in here, now it's neutral. That's the neutral atom. I could call that the number 2 atom.
You turn the camera.
Ah, thank you. And based on what I've said already, there can be 3 protons, which is eventually going to attract 3 electrons to make it neutral. 4 protons, attracting 4 electrons. What I'm describing is the periodic table. The number 1 atom has 1 proton in it. The number 2 atom has 2 protons in it. And let's talk about neutral atoms first before I start talking about charged atoms. So the protons and electrons balance. So we could call this the number 1 atom. We could call this number 2 atom. And then there's the number 3 atom, and the number 4 atom, and the number 5 atom, going all the way up to around 100. Actually, scientists through the years have decided that the number 1 atom is going to be called hydrogen. You can look up the history of these words. I forget most of the history, but it's kind of interesting. We call that helium because we discovered it existed in the sun before we discovered it on Earth a couple hundred years ago or whatever. So you've got a name that goes with the number atom. You with me? If you look, if you've got your periodic table, you can pull it out, but I'll bring one up here. So this is the periodic table. The periodic table that I will give you, if you look at the one that's on D2L, notice it's got the name and the symbol, like hydrogen, and then the summary symbol for it is H. You've got helium, it's He. The names and the symbols are there. I don't make you memorize these. It would help you to learn some of the first, second, third row ones just to speed up some of your process. But you'll have that whole thing for a test. So don't go around trying to memorize stuff. If it's slowing you down, just follow conceptually. I'll get to the other stuff that's on here. But so the number 3 atom, I should put positives on there. There's 3 electrons around it, 3 protons. And there's the name of the symbol. Kind of the next subject here is the fact that sometimes atoms will gain and lose electrons, and they'll become charged because they're no longer balancing the positive charge in the center. When that happens, but ignore that for now. Let's just talk about neutral atoms. What's the next thing to say? Oh, yeah, okay. So, let me just write this explicitly. What was I going to say? Protons, electrons, and neutrons. I'll mention neutrons in passing real quick. Neutrons do exist in atoms, and they show up in the nucleus. So, and you can have different numbers of, let me not go into neutrons yet, but that's where they are. Let's see. The number of protons never changes. The number of electrons changes following specific. What's fast? Same here. I'll say. Number of neutrons can change too, based on specific rules, but we're not even really going to talk about those rules. We're just going to talk about the fact that these can be different. This is where we spend most of our time. What electrons do is really, that's the world of chemistry. Atoms can gain or lose electrons. Electrons are involved in covalent bonding. Electrons are just like where we spend most of our time talking about atoms. Protons, the one thing I want to say about protons, and we'll end up not talking about it much later, is after the universe is like established all its atoms, and then they all exist through the universe. The atom that has 1 proton in its nucleus, it's never going to change. If you want to change the number of protons and neutrons in the nucleus, it can be done, but that's nuclear chemistry, and we don't tend to do much with that as chemists. That's, again, kind of the physicist world. You can get atoms to fuse together so the protons come together from two different atoms, or you get them to split apart. If you have a big atom that has 58 or 98 protons in it, you can smash it, and that's a nuclear reaction, nuclear explosion. We won't talk about that. So for this class, it's written in stone. If you've got an atom that has one proton in it, the number of protons for this atom will never change. It might gain or lose electrons or do some other stuff, but that's written in stone. So my point is, this is a synonym. Oh, let me tell you this. That number of protons in the nucleus, we call that the atomic number. And what I'm saying is hydrogen, or H, let me do this, hydrogen, H, 1 for the atomic number, those are like synonyms. If I start talking about an atom and I say its atomic number is 1, immediately you know that you can symbolize it with an H and you call it hydrogen, and it's never going to be anything else. So those three things are synonyms that go together. The number 1 atom, we chose to call it hydrogen, and what we chose as a symbol for it is H. There's another atom that has 2 protons in it. Its atomic number 2, that necessarily means it's called helium, and it's got this for its symbol, He. Those go together. And the thing to say about the periodic table, I didn't put the video back up, but the other thing that you can see here, besides the symbol, say for oxygen, symbol is O, the name of it is oxygen. You see that 8 right there? That tells you how many protons are in the nucleus. That's the atomic number. So what you're looking at for oxygen here is the first 3 things, oxygen, and 8, and the O are all synonyms. If I start talking about oxygen, it necessarily has 8 protons in it. It necessarily has a symbol 0, symbol is O for it. The twist, look at the book real quick and see what it does. I guess I'll have this because all books do this. We use Z for some reason to denote that. I'll use hydrogen as the example, just to keep it simple. Hydrogen, there are 3 different types of hydrogen. This is true about all of these that I'm about to draw. It's called hydrogen. It's symbolized H, and its atomic number is 1, which equals the number of protons. Always true about hydrogen. So let me put a proton here, an electron out here to keep it neutral. Hydrogens can gain 1 electron, which would make it -1. It can also lose 1 electron and make it positive, which is usually what happens. But here are 3 different types of hydrogen. But all of these, this is true for all of them. There's also a type of hydrogen that has a proton and 1 neutron in it. And let's just keep it neutral. And then there's another one that has 2 neutrons in it. But neutrons aren't charged, so to keep it neutral, all of these only need 1 electron to balance that 1 positive charge. Do you know what those are called as a group? You remember this? Remember the word isotope? That's 3 different isotopes of hydrogen. So you can kind of play games with numbers of neutrons, but for chemists, these come to the table already formed. When I say that you can change numbers of neutrons, well, chemists can't. So we never will take an isotope and change the number of protons or neutrons. Nuclear scientists do that, but we don't as chemists. It's only the electron we'll be concerned with. But that's what we call isotopes. You with me? All right. Do you remember the phrase natural abundance? Here's the thing. I guess I'm making masses. But the first 3 entries in this chart. Okay, table 2.4. The first 3 entries there are 3 different types of hydrogen. So you've heard the Big Bang Theory, the idea that all atoms and everything formed all at once, and it was all mostly hydrogen and a little bit of helium, and then those aggregate and force together and they make a sun, and then inside the sun, that's where you get the heavier elements. That's fusion, where like I said, we won't deal with this, but you fuse 2 hydrogens together, you literally have a helium atom. You fuse another one in there, now you got a lithium atom. So that's where all the atoms of the universe come from. And then here we are in our existence. They're all pretty much already formed. And here's the thing. The vast majority of, say, hydrogen out there is this one, with an electron around it. I guess I have to redraw these. In very tiny amounts, this exists, and in even tinier amounts, this exists. And that's it. There are rules about how many neutrons you can have, but that's, again, that's particle physics, and we won't go into the rules. But here's the thing. If you had like a magic device that could shoot out into the universe and randomly find a hydrogen atom, and just pull one in, and then the device shot out this way and got another atom and did that, and just sampled and got a huge sample, let's say hundreds of thousands of hydrogen atoms together. And you set that aside as a sample, and then you sat here on Earth and you went, okay, I'm going to go around my backyard, anywhere I can find hydrogen, I'm going to get 100,000 of those together. Either way you do it, the proportion of this to this to this is always the same. If you shot out the universe and you just got 2 hydrogen atoms, you shot out the universe, you got 2 from over here, and you got 2 from your backyard, there's a good chance that they're going to be different. Like some of your samples, when you do that, you'll have 2 of these most of the time. But every now and then, you'll have a sample that has these 2 in it. And every rare now and then, you'll have a sample that has these 2 in it. But if you get hundreds of thousands of them, it balances out. It's kind of like if I said, like if average heights, what's the lower end of average heights? What would you say? I'd say at somewhere around 6 feet, and what would it be? Let's just say 4'11". And I said, okay, I'm going to predict the next person that walks through their door, I'm going to predict their height. If I say a very specific height, the odds that I'm going to get that one height are pretty low. I mean, if I said, okay, I'm going to say they're 5'4", what do you think the odds are the next person that walks through that door is 5'4"? Pretty low, right? But if I said, I'm going to stand here and wait till 100,000 students come through there and get the average, I can just use the average that anybody has done by sampling enough people, and I'm probably going to be right about that average. So when we talk about these, on average, there's most of these in any sample of hydrogen, a small number of these and an even smaller number of these. So what I'm saying is, I'm trying to lead up to molecular mass. Let me get a picture of this. So the next subject is, how much do these things weigh? And really, I guess we'll talk in terms of atomic mass units first. So if you scooped up hundreds of thousands of my phone is freaking. We call this the atomic mass unit. And this one weighs that much. This one weighs protons and neutrons weigh almost exactly the same, and electrons are so much lighter than protons and electrons, you can almost figure out what this number would be just by the number of particles in the nucleus. There's only one here, that's the weight of the proton. This is close to 2 times the weight of a proton. It's a proton and neutron. This one is 3. You won't have to memorize these types of numbers. I'm really just trying to paint a concept here. All right. That's how much these weigh in their natural abundance. 989%. If I randomly got 500,000 hydrogen atoms from my backyard or from the universe or wherever, 99.989% of them are going to be this type. And then in very tiny amounts, and that's a percentage, 0.0115% of a group of 500,000 hydrogen atoms will be this type. This one just says trace, so 0.00000, something like that. Here's the thing. If you do grab a sample of, say, 500,000 atoms, you can predict how much they'll weigh by using the average. So if I do, I'm going to turn these into fractions, which just moves the decimal 2 places. 0, move it this way. 0.000115. And the trace I'm just going to ignore. Times plus 0.000115 times 2.0141. So this is like a weighted average of this. If I calculate these out, this equals, if I follow the rules, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2, 3, 4, 5, do that if I'm following the rules. 5 times 2.0141. But really, following the rules, I've got 3 significant figures, so I'm only keeping these. So this one, I'm just going to do that. This plus this. Plus 1. The weighted average I now have is something wrong. I left the zeros off. 0.00115 times 2. Tom added these two together. If you add those up, you get 1.01. And that's what you see on the periodic table. 1.01. So what that is a weighted average. All right. Now follow me here. For hydrogen, I want to get away from isotopes because they really don't do much for us. That's a very, 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 very tiny measure of mass. But if you multiply that by some constants, and you're careful how you do it, this actually, I don't want you to think of this as atomic mass units. I want you to think of it as grams per mole. Do you remember that? Grams per mole. You call it atomic mass when we're doing it for molecules, we'll say molecular mass. But the point is, mole is, it's like dozen. I'll go over mole another day. But since that's an average, you can say, I got a bunch of hydrogen atoms here, and if I weigh them, they weigh 12.6 grams. But when we're doing chemistry, we need to know how many of them, not what they weigh in aggregate. So you can use grams per mole, and I'll again tell you to go. I'll go into mole another day, but I want to know what that is in moles. It's kind of like, if you've got 24 cars, you have 24 cars. It's a counting unit that means 12. If I have, let's say I have 10 shoes and I want to pair them up, that means I can make 5 pairs out of the 10 shoes. The number is 2 for pair. Score is 20, so if I have 40 things, I have 2 score. If I have 60 things, I have 3 score. Mole is like that, and I'll go into it another day, but if I take this and flip it over, using this average, weighted average, this is still going to work out to tell us how many. It is kind of approximate, but it's that's what my calculator says. 3 significant figures, 3. I keep these 3. So I know I have 12.5 moles. And that does tell me by number how many they are. But I will tell you to think of this when you look at the periodic table instead of the AMU, because really we talk about it very briefly when we talk about isotopes, and then we never talk about it again. This is kind of where the rubber hits the road for chemistry. We're going to stop and do that lab in a minute, but let me see what I have for these quizzes, and then we'll go into what comes next. I'm going to tell you the ions. One more thing about isotopes, and you just kind of walk away from it. Let's see what I have here. AG. Do you know what AG is? It's silver. So that's the symbol for silver. And that's typically the way we write it and the way we leave it. But there is another way to represent these when you want to talk about isotopes. Let me just write this up here now. 7. So if you see Ag written like this, it's specifying one of those isotopes. Bring up a periodic table again. There's Ag right there. You see it? How many protons are in the nucleus for Ag? 47. And that's what this is telling. So do you have your eyes on Ag there? This one here, see this one? What is the atomic symbol for an atom that has 42 protons in it? Just look at the periodic table. There's 42. That's the atomic symbol. It's called molybdenum. Fun to say. All right. There's the symbol. Up here is the protons plus the neutrons. Down here is the number of protons. When we get to ions, we'll put an ionic charge up here. But this works out to 1 to be negative. In some sense, that's electrons minus protons up there. I'll get to that in a second. So if you see this symbol and you're asked, how many neutrons are in that specific one little atom there? Since this is protons plus neutrons, and this is protons, you just subtract. So 100 minus 47 is what? I can't do it in my head quickly either, but I happen to do that one. It's 53. This is protons plus neutrons. This is just protons. But because this is protons plus neutrons, and this is just protons, if you subtract protons from the number that's written up here, that'll tell you how many neutrons. Based on what I said before, those two things, the 47 and the Ag, it really is totally superfluous to write them both. If it's Ag, it necessarily has 47 protons in it. That's what humans have chosen to call the one that has 47 protons in it. But it is still written that way. I don't know why. So you might get questions like that. Another way, so this is how you specify a particular isotope, which we won't spend much time doing. There are uses for isotopes in chemistry, but usually you're a physicist when you're talking about neutrons, isotopes. Another way you can write that, like you might see that written somewhere, and it's specifying a specific isotope. It's the isotope that has 53 neutrons in the nucleus along with the 47 protons. Another way that's written, that's one way it's written, but sometimes you'll see which just straight up tells you the number of protons. This is kind of why I like to have the periodic table on you. So I have to keep going back here. So you might see it written that way, you might see it written this way. If I gave you this and I said, silver 53, how many neutrons are in silver 53? It's right there, that's the number of neutrons. If I said, how many protons are in silver 53? How would you answer? You pull out your periodic table and find silver, and it's going to say on there 47. Okay, let me move on to electrons. And let's not do silver, let's do, you want to do this. Hydrogen is up here in the corner. Okay, that's the top row. Just so I don't have to keep going back there. Hydrogen is 1, so that's the atomic number, the number of protons. So now we're getting really to chemistry. And then there's this big gap. So I'm going to build us a little periodic table here so I don't have to. Hydrogen sits here. And here we have helium, which is atomic number 2. Okay. I'm going to have to go to the periodic table again real quick. And here's your first sort of big definition. So if you look at the periodic table, you see the stair step that goes down here on the right? So kind of your first rule to realize, to learn, is in that top right corner, this triangle that's cut off. And I'm actually ignoring this far right one. The helium, the neon, argon, those are called the noble gases. So ignore those for this. Everything to the top right of that stair step, those are called non-metals. Those are the non-metals. Along the stair step, some of those are called metalloids because they sometimes behave like non-metals and they sometimes behave like metals. Let me ignore those for now. Everything else that's not in that top right triangle, hydrogen is actually a non-metal too. It happens to be way over on the left on the top. But those are your non-metals. Everything else. Okay, some of them are metalloids. Okay, but truthfully, there are some that are called metalloids, not metals. Okay, knowing that, non-metals you remember this from previous chemistry? When you decide what ions are? Still putting you all to sleep. You remember ions? Okay. Ignoring boron. Let's just focus on these. I'm going to ignore the ones that are right on the stair step. But all of these are non-metals, and let's not count these. Okay. Nitrogen. How many protons does nitrogen have in its nucleus? For the neutral atom, 3, 4, that's 7. So this overall thing is neutral. These are all positive charge. All right. Nitrogen, this is neutral nitrogen, and it exists. Neutral nitrogen will be in molecules. But like I said, the next subject we bleed into is ionic compounds, so we need to talk about the ions. Do you remember what the ion form of, what did I do, nitrogen? Do you remember? I'll tell you. You put your finger on the non-metal, and then you count out to the right of the periodic table. But you don't, this is important, you don't count nitrogen. You go like this. There's nitrogen. 1, 2, 3. What that means is it gains 3 extra electrons. It's gained those 3 extra electrons. Now what's its charge? It's 3, it's negative 3. When it was neutral, the 7 positive charges canceled out the 7 negative charges, so it was neutral. But nitrogen tends to gain, it can exist neutral, and it can also exist as an ion. If it's an ion, it's necessarily going to be 3 negative. I say negative 3 a lot. I don't know why chemists decided to put the negative sign on the right side. Nitrogen. And you can do this for all the nonmetals. Based on what I just told you, what do you think the charge on oxygen is when it's an ion? We don't count oxygen, we count to the right. We go 1, 2. That means it'll gain 2 electrons. So oxygen can be -2. There's sulfur, there's phosphorus, silicon. This is chlorine. Argon goes there. When chlorine is charged, when chlorine is charged, what do you think its charge is? It's -1. You put your finger on chlorine, but you don't count it, and then you move to the right. 1. It gains 1 extra electron. So, now that I've explained that, you can pretty much memorize that anything in this column, you're going to be counting over 4. Anything in this column, you're going to be counting over 3. You'll count over 2, count over 1, and these don't ionize. That's why I said 2 on 1. So putting those as headers to those columns, any of the nonmetals down below here can exist in its neutral form and in a -4 charge. Any of these can exist in its neutral form, or it can exist as an ion as a -3 ion. It's sort of the reason ions are important. I'm going to do the metals next. Once they form ions, once this gains an electron and once this loses an electron, then they'll stick together, and that's what an ionic compound is. Different from covalent compounds. Let me do the metals though. This is where aluminum is. Metals, and this metals is anything that's not in the top right corner. So everything down here in the fat part and everything in these first 2 columns, those are all metals. Metals tend to lose electrons, not gain them. But you see these in the fat part here? The periodic table here has 3 through 12, columns 3 through 12. Ignore those for now, but those are metals. They're just called transition metals. And let's focus on these first 2 columns. Let me write a couple more of these. Potassium, calcium. Let's just stop there. And I guess I'll write the potassium, calcium. This is 19 and this is 20. When you're talking about the metals, they tend to lose electrons. So you can still point at them on the periodic table and count to figure out how many they're going to lose. For the neutral magnesium atom, how many protons does it have in its nucleus? 12. These are the atomic numbers that I've added here. Building it on the board. Not put the video back. Okay, so we've got neutral magnesium. If it's neutral, it's got 12 protons and how many electrons? If it's neutral. If it's got 12 positive charges in the nucleus, how many negative charges does it have if it's neutral? 12. They have to balance. If it's neutral, if it's not charged, that means it has exactly as many negative charges as it does positive charges. So neutral magnesium has 12 protons in the nucleus and 12 electrons going around it. That's its neutral form. If you had a bunch of magnesium aggregated together and they're all neutral, then you, I erased it. Then you have a metallic compound, which, like I said, we won't talk about very much. But if it's charged, now you have to ask yourself, how many electrons will it lose? If it's got 12 protons, and I'll just say 12 electrons going around here. It's neutral. If it gains electrons, if it loses electrons, it's going to lose some of those 12. How many does it lose? It's different from when you count over here. When you're counting over here, you put your finger on the thing you're counting, and you do count that. So magnesium loses 1, 2 electrons. And these here lose 1. You count the 1, and you're already at the end, so it's 1. So everything in this column can exist as if magnesium loses 2 electrons, so now it's 10 electrons, what's the charge on it? These became negative because they were neutral, and then they gained some negative charge. This loses 2 electrons. That means 10 of these protons are neutralized by these 10 electrons, but there's still 2 left over in the nucleus. So that makes this charged 2+. You follow that? Gaining electron or becoming negative is intuitive and obvious. It's a little subtle, but when you lose electrons, you can't change the number of protons in the atom. So if it loses 2 electrons, that's going to leave 2 protons unneutralized by the negative charge. So that'll be +2. So really what it comes down to is hydrogen's weird. It can lose an electron and become positive, or gain an electron and become negative. Most of the time, it's for our cases, it'll be the positive. But everything in this column, when it's an ion, will be +1. When this is an ion, it's 2+. When these are ions, 4 negative, 3 negative, 2 negative, 1. So now, if you have periodic table in front of you, and I walked up and I picked one of these, or one of these in the top right corner, I said, what is its charge when it's an ion? It's really that simple. Everything in this column will be -4, everyone here, -3, -2, -1. Everything in this column will be +1 because it loses one of the negative charges. This one will lose 2 negative charges to become +2. You with me? Basic fundamentals of atoms. There's one more to stick in here. There's that fat part here I haven't talked about yet. Transition metals. Leave that for now. Aluminum is the only other one to include here. If I'm counting to the left, and I just skip this gap that's there, I'll go, okay, there's aluminum, and it goes with the metals. It's a metal, it's not even a metal wood. So it's kind of the one odd one out here. But I would go 1, 2, 3. So ignore boron for now. But if I said, okay, of all the metals that exist, all the metals on the periodic table, ignoring the transition metals, you can tell me what the charge will be. It's a definite known charge, and it's never anything else. These will never be +2, they will never be -3, or anything, always just going to be +1, or neutral. These will always, always, always be +2 and no other charge. Aluminum will always, always only be +3. It'll be neutral, or it'll be +3. Nitrogen and phosphorus only ever 3 negative. It's never anything else. And the reason I'm stressing that is it's the transition metals. Gotta bring this up again. So all of these in this fat part down here, those can take on more than one charge. Like sometimes you'll walk up to, there's vanadium, the V right here, column 5. It can be, and they're always positive like the other metals. So vanadium can be +3 or +5 and a few others. So you can't walk up, I can't ask you, I can't say, so Cr is chromium, top one, column 6. I can't on a test say, what is the charge on chromium? Because you can't know. See what I'm saying? But I can ask you, what's the charge on sodium? What's the charge on magnesium? What's the charge on oxygen? Those are definite. You with me? Let me look real quick at these quizzes. Back it open up. atomic mass. Yeah, whatever. I'm going to open these so you can practice these. So do get to these and practice. This is how you know if you're ready for the test. And it's best to keep up as we go. This is here. We'll get to ionic compounds next. So I'll leave it at that.